Okay, so the first thing when I started the project, the first thing I set up was the character movement. Since my character was a phoenix, my main character movements were flying, which also involves moving forward, upwards, left and right, as well as rotations. So the first thing we'll look at is how I set up the character movements. The first thing I did was create some input actions using Unreal Engine's latest enhanced input mapping system, which is in, as you can see, Phoenix third person mode input system. And these are all the input actions that I created: AC move, IA look, IA move vertical, IA turn, and as well as the main input mapping context where all the mappings has been done: WASD, left shift, IA turn, and all the mappings have been done here. Since I've got this set up, I'll move on to Phoenix character controller. This is where all the movements have been set up in the blueprints. So we'll look at the forward plus horizontal movements. This uses the AC move input action that I just showed you. It takes in it uses the action value and breaks it into XY values. I'm also, as you can see, storing these XY values so I can use it at different places wherever I need it. I'm using some checks to see if the values are smaller or larger. The main thing done here is getting a forward vector and a right vector. Multiplying this forward vector and a right vector, you can get a strafe movement, as you get a forward movement, left right movement, as well as strafing. So the multiplying these two does the job of strafing as well. Now we'll look at the left right movement. Sorry, we'll look at the vertical movements. This uses the IA move vertical input actions. Once again, it just breaks up into three vectors x, y, z, and I only need z vector for the upwards movement. Uh, I'm using the up vector and multiplying it with the z that I get from the action value and setting it to the vertical movements variable. With with the movements done, we have character rotation next, which uses the IA turn input actions. It uses the same y value that are stored here. It multiplies y value with the rotation speed. This rotation speed is just a scalar value. It's currently set to 0.15 because that's what I went with. You can adjust this to change how fast the Phoenix moves. And finally, the output value is what I attach to the add controller yaw input. So this is what gets me the Phoenix character rotation. Just to make the upwards and downwards movement of the Phoenix a bit more realistic, I use the timeline feature of the Unreal Engine, and this is how I'm doing it. So this is first we look at left right tail. This also uses the IA turn input action, quite similar to the character rotation. I'm using the same y value that I showed you earlier. What this timeline does is this interpolates between the y value. This is a great way to interpolate between y value smoothly. I'm using the tilt amount. As you can see, this is how the curve looks. It's currently set to 0.5 length. And once you multiply this tilt amount with the y value that we had earlier and attach the output with the role of the make rotator, The Y pitch here that you see is coming from another tilt, which is up down tilt. It uses IA move vertical input action. This uses action value and breaks it into three vectors, and I only need Z1 for the up and down tilt. So what I'm doing here next is just the same thing. Timeline. I'm using the same timeline thing. This also has its own tilt amount, which is slightly different from this tilt amount. Once again, I'm multiplying it with the Z value because that's what I need for upward and downward tilt. I'm assigning it to the Y pitch. This makes up for both the upward downward tilt and left right tilt. And the output is assigned to the set relative position. This is what gives me tilt on my characters. And as you can see, it also takes in target, which is coming from the mesh, and this comes in from the Phoenix character ref. Phoenix character ref is another blueprint just for the character. So and this is where it comes from actually. So as you can see, as soon as the blueprint starts, using the event begin play tick, I'm casting some classes here and storing them as variables. So this is Emberflight game mode ref, this is Phoenix character ref. So I don't have to cast again and again in different event graphs. I can just use the stored reference of those classes that I need. Uh, at the end, we also have camera rotation. For this, I'm using IA look input action. As you can see, same again, it uses Phoenix character ref. There's also spring arm. This spring arm comes from Phoenix character ref, as I'll show you. So this is the Phoenix BP Phoenix character, and this is where the spring arm comes from. The camera is attached to it. The spring arm helps in being attached to the character all the time, so you can move your mouse freely around your character. Uh, this gives a relative rotation, which is what I need. I'm breaking this rotation into, once again, roll, pitch, and yaw. I'm multiplying with some negative values. This is to clamp it properly, both the pitch and the yaw, and then I'm creating a make rotator again and just assigning it to the set relative position. Then this helps in rotating the camera. Set relative positions right here. Fine. Just before we move on from this BP Phoenix character controller, you can see there's wind field which affects the Phoenix. There will be a further video that explain where these functions come from, but for this video I'll only explain how I'm making this my wind vector field influence my Phoenix character. So this again uses a game mode ref, uh, which has an wind field instance stored in it. This wind vector field has a function called sample wind at position. It takes in world position, and the world position is of the character or Phoenix. So which comes from get control point, get actor location, and the return values attached to the world pos. This is a scalar value. Wind influence strength depends on how much I want my wind to affect my character. I can just change it right here, and I'm assigning it to this variable, final wind influence. And this thing here is the debug. If you want to see which direction the wind is flowing and you want to visualize the wind field, this is it. Currently I've set it to false. I'll show you if I turn this, I can have visualize my wind field here. So now that I have both all three of my influences that I want to be affected on my Phoenix character. So these are the three: forward and horizontal movement. Vertical movements come from here, and the final wind influence comes from right here that I just showed you. I don't want my wind field to have a larger effect on my Phoenix, which is why I'm multiplying it with a slightly smaller value, which reduces the effect that my wind field is having on my Phoenix. And after adding it, all of three of them together, this works in sync. I can move my character using WASD key, and my character is also affected by my wind at the same time. So this output value is being attached to the world direction of the add movement input, which takes in. So next up, we have the wind vector field class. This is a blueprintable class because I wanted it to be exposed to the blueprint, so I can assign things there and have my functions like sample wind at position, which has been used in BP Phoenix character controller, as well as the custom Niagara data interface. Inject wind at position is used for local wind motors, and the update function is also a blueprint callable function. It is called from BP game mode ref. So as you can see, this is BP Amber Flight game mode, and I'm using an event tick to call this update function every 0.2 seconds. This takes in the target wind field instance. Wind field instance has the wind vector field class assigned to it since we made it blueprintable, so it shows up here in the Amber Flight game mode ref. Now let's get back to the class again. We have some parameters that can be tweaked, like field origin, size x, size. This is the sizes of the grid and cell size. This can be tweaked to increase the resolution, whether you want more resolution in the field or outside the field. Wind noise frequency, wind noise seed, scale, bias. Bias is what uh, what changes the direction of the field. This is what controls the wind direction the way you want to. This is once again noise-based turbulence. You can control the strength. All of these stuff is being used in the update function, which I'll show you in a second. Post load and post edit change property. I'll tell you when we move to the .cpp what are they supposed to do. These are some private variables. This is the main simulation grid, velocity grid. I'm using the fast noise light generator because it's easy to integrate and it provides some great noise types to be used for having different kinds of noise that you need. And these are just some helper functions. Two of the important ones here are advect and decay velocity, sample wind at grid position. Now we'll move to the .cpp class. Just an empty constructor. This is the first initialize function. This is where the grid is initialized. As you can see, for the global wind, I'm calling the initialize function right from the .cpp, just to show you that the grid can be initialized from the code as well as from the blueprint. So this is the Amber Flight game mode .cpp. This includes a pointer to the wind vector field instance. So as you can see, in the begin play, it initializes the wind vector field. This is the one that I just showed you. And just previously I told you about the post load function. The Niagara system, and the Niagara particle is entirely viewport based. So as soon as the Unreal Engine loads, they need values, otherwise they won't simulate, or they won't move and won't react to this wind field at all. So one of the ways that I found to do this is post load. As soon as the Unreal Engine loads, this warms up warms up the wind vector field. So as you can see, it's calling the initialize function. Earlier I had this warm up wind field here instead, but I thought just to move it here and make it a bit more readable, and just call the initialize function in the post load. So as soon as the Unreal Engine loads, it calls the initialize function, warms it up with some velocities. Uh, it runs the update function quite 10 times. Uh, these are some helper functions down. Get index is validate index, which I'll show you where they are used. So the first thing we'll look at now is the update function, which is where all the simulation happens. When simulation happens, it calls, if the velocity grid is num, it just returns, and it has two functions, advect and decay velocity. We'll look at the advect first. This is the function that's supposed to transfer the velocity across the field smoothly, and it does it by using a temporary array to hold the new velocities, and then just replaces it with the old velocities. This uses a trilinear interpolation, which has been done here in sample velocity at grid position. We'll have a look at it. Once again, just a return function for the safety check. This does a trilinear interpolation by interpolating at all the eight corners of the grid cell. And that is what the advect function includes. Next, we'll look at the decay velocity. It's just a small, simple decay function that just decays the velocity over time. This is just set to 1.0 f, which is what I need for my wind vector field. We'll go further down the update function. So this is a for loop that loops over the grid and changes the velocity based on the values, the noise values, especially the noise values, that turbulence x, turbulence y, turbulence z. It gets its noise from the get noise function of the Perlin noise of the fast noise light that we have here. This is where it gets its noise from. If I go up, you can see this is the type I'm using, set noise type, which is currently set to noise type open simple x2. It also takes in frequency and noise seed, and I've set it to some default values. These are the default values for them. Moving further down the update function, just assign those values to the turbulence with a scalar value, turbulence strength, which multiplies with it. This controls how strong the turbulation will be, and you can tweak this setting in the Unreal Engine, since I've exposed it to the blueprint. We finally assign all the stuff to the wind velocity, which includes turbulence and wind scale, and finally we put the wind velocity back into the velocity grid at the index, at the accurate index. Next up, we have inject wind at position. This is what's being used for local wind injector. Local wind injector uses this function to inject velocity at the specified position, and that's all there is to this function. sample wind at position. This is the function that's been called at many different places. One of which was BP Phoenix character controller. We were required to sample the wind at that position and make the wind affect our Phoenix character controller. So it just calls the sample wind at grid position, the one I showed you earlier. This is the one. It uses the trilinear interpolation methods. And finally, we have a debug draw method, which I'll show you how it works soon. And then there's a reset field method. This has been specifically introduced for the custom Niagara data interface that we'll see further. Even if there are certain functions in the custom Niagara data interface where even if you change the value, the particle keeps following the old values, since the values are never cached or they are never reset. The values are kept cached somewhere, and instead of being overwritten, the new values are just written on top of it. So this is what I needed. I needed to reset the field, and this is being called every time a property has been changed. You can see as soon as a property changes, the field reset and it marks the wind vector velocity as make package dirty. That the wind vector field has been changed. This is what it is, Unreal Engine. So this is all there is in my wind vector field class. We'll go in Unreal Engine now. So when setting up the custom Niagara data interface, there's an example provided by Unreal Engine. It doesn't go into that in depth as it should have been, but it does pretty well to explain what stuff do you need to start your custom Niagara data interface. And the first thing is the amberflight.build.cs. This is a file in the Unreal Engine that you need to modify. You need to include these things: Niagara core, Niagara shader. If you are doing the GPU simulation, which I am, you also need render core and RHI, and just some more Niagara stuff. And this is one of the third-party fast noise light that I'm using in my project. But this is all the Niagara stuff that you need in amberflight.build.cs. Next thing we'll see, we need some more stuff. This is the mean file amberflight.h of my game. These are the two functions that you need. If you look at the example code provided by the Unreal Engine, this is what you'll see. They take in two virtual functions, which are startup module and shutdown module. This class needs to be inherited by this class inherits f default game module impl. This is needed. This is where these virtual functions come from, and it also includes a void functions a void function that lists all the Niagara data interface faces in the output log of the Unreal Engine editor. This is what I use to debug whether my custom Niagara data interface was successfully registered or not. Now we look at the .cpp file. Yeah, so this is, you need some headers on the top to get these things working. So you need this macro that registers your Amberflight module. Then this is the function, startup module function that integrates your custom Niagara data interface with the Niagara's own data interface managing systems. This is where it's all managed. You need this register asset type action. Without this, your Niagara data interface won't register with the Unreal Engine system, and it won't show up at all when you click on right click on user parameters, common and data interfaces. You can see all the other data interfaces, but you won't see your own custom Niagara data interface. So you need this register type action, and shutdown module doesn't require much. You can add for better exit, but it doesn't require much. This is you need the main thing you need is to register your in vector field with it, and this is the list all Niagara data interface function. And I used to call it here in the Amber Flight game mode ref while debugging, but currently I've just, since I know my custom Niagara data interface is integrated with the Unreal Engine, I've just commented it out, but you can uncomment it to see my custom Niagara data interface listed in with the other data interfaces. So this is pretty much all you need to get started working in the Niagara data interface. Now we'll actually look at the Niagara custom Niagara data interface WinField that I created. So we'll start with the header file. Finally, we'll have a look at our custom Niagara data interface WinField. You need a couple of headers, especially if you are using the GPU simulation in your custom Niagara data interface. And let me tell you this stuff. All the parameters in the U class is absolutely necessary if you want to see your custom Niagara data interface being displayed in the Unreal Engine. If you miss some of these parameters, your custom Niagara data interface won't show up at all. So the first thing you need to do is make your custom Niagara data interface WinField inherit from the Niagara data interface. This is the interface that gives you all the virtual functions that you need. First of all, it includes a constructor. It's just an empty constructor. And this is one of the important functions, sample wind@location function. So I'll go one by one what it does. Sample wind@location function is a function which directly belongs to the Niagara's VM. What it does basically it directly queries the uWin vector field class that we saw earlier, and at any given world position that we feed into it, like this XYZ, these positions are filled into it from the ScratchPad module, from where I assign the particles dot position to these X, Y, and Z values, and it outputs the velocities. It samples velocities at that position and then outputs it further. So this is what it is in the sample wind@location function. As you can see, it calls the sample wind@position function of the WinField that we saw earlier. This is the sample wind@position function, which it calls directly from here. And then we have get function, and get VM external function are two of the most necessary functions in this custom Niagara data interface. First, we register our function. You can just directly include the name of your function as a text, but a better and more readable way to do is by declaring as a static const at the top, as well as any of the path that you need. So just to keep your custom Niagara data interface overall clean, and then you need to add the inputs of your data interface class. This is the WinField. This is one of the things the user dot parameter, you need to create a win vector field using user dot parameters in the Niagara editor. So when you create your, and what you'll get is the custom Niagara data interface. If you go to user parameters, you click on make new data interfaces, and you can see your data interface being listed. Just click on it, and then you'll have the you have to assign your win vector field class to the user parameter. You'll have to assign your win vector field class to the parameter, and this is how you do it. So you can see there is an object pointer here, and this will, as soon as you create the user parameter, you will have this win field waiting there to be assigned. You have to assign your win vector field class there. And once you have your user parameter ready, it's your user parameter that you connect to this win field class in the ScratchPad module. So this linking is most important. From user parameter to the input dot win field, this one. This is what links your Niagara editor with your custom Niagara data interface. And these XYZ values right here, like I said earlier before, these are provided by particles.position using the map get node in the ScratchPad module, and the out x out y z. These are the velocities. These are combined in the ScratchPad module using a make vector, and then assigned to the particles.velocity, which further assign those velocities to the position to make the particles move. And then we have a couple of registration that we need to do, which is it a member function? Yet yes, it is, and a bit of and some other necessary registration like requires context, and then these two are important. If you want a CPU simulation, you need to make it true. If you need to have a GPU simulation as well, you need to assign that to true as well. And then just a small description. If you hover over your custom Niagara data interface in the Niagara editor, this is what you'll see. And then we just output those signatures. And then we have get VM external function. This is what registers the function. As you can see, binding info dot name and sample winfield name is the name of our function. This function, sample win at location functions. This name should be accurate. Any error in this name will fail to register your function with the custom Niagara data interface and the Niagara editor overall. So you need to do this if binding info dot name is equal to the name of your function that you want to register, and then this is how you bind it. This is how you bind it and expose it. You just give your class name and the function's name, and you bind it using this. Next up, we have our copy to internal function. This is a very, very necessary function. Even if you have everything else correct, your custom Niagara data interface will show up in the Niagara editor, but it will give you a binding error, and the binding error will look something like this. This is what it will look like. Your function sample win at location that I have in my custom Niagara data interface won't bind properly, and it won't bind properly because my custom Niagara data interface stores and uses a U object, which is the win vector field object. What copy to internal does is it duplicates the Niagara data interfaces during system compilation and things like editor operations, script execution. If the copy to internal function isn't overridden and isn't implemented here in the .cpp, this is a virtual function. I need to remind you, this is a virtual function and it needs to be overridden. If this function is missing, Unreal will just use the base class defaults. So you 100% need this function, uh, because if this function isn't there, then your win vector field won't be properly copied, which will result in the binding failures or incorrect script compilation. Just as I showed you this error right here, you'll get this error or any similar error for your function, or it will also have a broken per instance data when you try to implement your GPU simulation. Next up, we move on to the equals function. And the equals function is just another virtual function, and it checks for equality between the current instance and another instance of the custom Niagara, not the custom, the actual Niagara data interface, the base class Niagara data interface object, by comparing their wind field with with the current with the wind field of the current instance. But for that, this needs to be safely casted right here. Now, can execute on target is a pretty self-explanatory virtual function. If you just need the CPU sim, this is what you can do. I've added a comment for that here. Target is equal to e Niagara zip target and CPU sim. You can just have this if you need a CPU sim, or if you just need a GPU sim, you can have this much and replace the CPU sim with a GPU sim. But since I needed both, I'm using both in my custom Niagara data interface. I'm returning true, and this is what you need to do as well if you want both of them. And next up, we have post init properties. What it does is it initializes all the properties for both of your class default objects as well as non-class default object. It also sets up a proxy. This proxy comes from Niagara data interface. As you can see, if I click on it, this will take you to Niagara data interface header, and it's a unique pointer to the proxy, Niagara data interface proxy. And it sets up some flag as well. This will allow any kind of variables. Yeah, your class and functions can have any kind of variables as well as the parameter. If you're connecting your which user parameter to your wind field, which I am, this needs to be allow parameter flag set here, and then we just register our custom Niagara data interface class with the Niagara's registry. This is what will register our custom Niagara data interface with the Niagara registry. And I think I showed you earlier the list all Niagara interfaces. This one, if as soon as you are post init property register your class with the registry, it will start and you output it. It will start showing up in your output log. Your custom Niagara data interface will be there in your output log. So this is pretty much what you would require for your CPU sim. So next up, we will look at the GPU simulation, and what all stuff do you need for it. Now, see, you need a couple of things for your CPU sim, which is almost this much. Uh, Instance data, because you'll only need your instance data. data is a struct which includes a wind field pointer. This is what you'll need, and the rest of the stuff is for the GPU simulation. Now we'll actually start with the GPU simulation explanation and what all functions do you need and what and how they are implemented. Since we have what in it per instance data does and the destroy per instance data does is it manages per system instance data, and it also stores the references to the wind field for sampling. You need to store the references somewhere, and this is where it's stored, and this is where they are freed in the destroy per instance data. And after you store all the references for the sampling and you take the data from your wind vector field, the actual GPU simulation stuff needs to be done, especially the functions that you would require for it. The first one is append compile hash. Uh, what it does is it registers all your parameters, all your parameters as well as your .ush file. .ush file is where all your HLSL code lies. So I'll show you what it takes. Uh, it first calls the super append compile hash function of the Niagara data interface, and then it will register your shader file with it. This is the path of my shader file, which is in plugin experimental chaos Niagara data interface windfield.ush. So I'll show you how the .ush file looks. This is how the .ush file looks. It takes in, we need to declare all the parameter names above from the shader parameter struct. You can see the shader parameter struct here. This is the GPU shader parameter struct, and you can see all the names here needs to be matched with all the names here. We are also using a structured buffer. I'll show you how that is used, but this is our .ush file and the part to it, and then we have our shader parameters. You need to update that as well in the update compile hash. This is just our shader parameters. So and the next thing after append compile hash is the get parameter definition. HLSL, it will take all the data from the .ush, and this will be replaced. This slide, this is just an empty body. This template args will be replaced by this .ush code, all of this stuff. So this is, you just need an empty body here. And the get parameter definition HLSL, and get function HLSL is what mimics your sample wind field or calls your sample wind field sample wind at location function on the GPU. So you need a function that does a call to the sample wind at location function, and this is where it happens. You provide an HLSL template. This template needs to be accurately matched with your .ush file. So this is a macro that defines the sampling function, which accurately matches with this one. And then this is the function that calls the actual function, sample wind texture. This sample wind texture is what does the sampling job on the GPU side. If you want, you can also just whether the system works or not, you can just add velocity dot x is equal to 50 or 100, and you can see your particles moving, and set the Niagara emitter to GPU sim, and you can see the particles reacting to it if you add any hard-coded values here as well instead of just the procedurally generated win values. So the next thing we have is build shader parameter. That this builds all our shader parameter struct. So while the other functions passes those shader parameters, this is the one that builds it. Build shader parameter function does the job. Now you need to call dot add nested struct. You can also just do it individually. Shader parameters dot, and there are functions where you can use to register your variables individually if you need to, instead of just using a struct. But struct is if you have a lot of variables, and this is the better way to do it. Uh, then finally we have our set shader parameters function. Just before we move on to set shader parameters function, one thing about build shader parameter is it defines all the shader visible variables, such as all the way all of my stuff in the win vector field, like field origin, size x, size y, size z, all the stuff that is needed, like this. These are all the stuff it defines all these variables, as well as an SRV pointer for our velocity grid. So now we move on to our provide per instance data for rendered thread. I'm going by sequence. This is the first thing that executes when we talk about GPU simulation. Once all this stuff is done, get parameter definition HLSL, get function HLSL, append compile hash. We'll go sequence wise. So build shader parameter is what executes first, and the second thing that executes is provide per instance data for render thread. This packages per instance render data, like the grid pointer. I'll show you what it includes. It includes a pointer to our grid. It needs to be vector 4f because there are forums online that says there are misalignment issues between the way things are. The memory layout works on the GPU side. So sometimes if you use a 3f, the 12 bytes padding alignment would mismatch with the 16 byte padding alignment. So it needs to be 4f, as many of the tutorials actually use 4f instead of a 3f. So this is all the render data includes. It also includes a pointer to the asset buffer. We'll see that in a bit what it does. No, so it packages all the render data, as you can see. All the data from the instance, the field pointer is assigned to the render data, and then it packages and sends it to the GPU. We also assign the asset buffer as I just showed you, the asset buffer. Finally, we have our before we go on to the rendering thread, we have our set shader parameters. This binds our velocity grid SRV, as you can see. Now that we have passed from CPU to GPU, we'll pass that not GPU but the render data, and then we pass the render data stuff to the shader parameters. This is where we need to pass all of this stuff to the variables or parameters that is being used in the HLSL or on the GPU side. And then we have our SRV from our GPU buffer. The what say set shader parameters main purposes is to find the velocity grid SRV and field parameters to the Niagara's compute shader. This is very important. Get SRV or default float for, because the other custom Niagara data interface, the other Niagara inbuilt Niagara data interface also use it. You need to provide some dummy values or a default float for. Otherwise, it will have all the zeroed values on the HLSL side, and you won't see your particles moving at all. It needs either get SRV or default float or some similar function. There are a couple of other functions for other kinds of buffer as well. So this is just the logging stuff. Mhm. We'll also have a look at per instance tick, because it is the tick that runs. It is the function that runs every tick. Now this holds a pointer to the instant data owner, which resides in the instance data struct. And I'm using double buffers, just to avoid having zero values at any point. I'm using double buffers and I'm writing to it in the way. As you can see, I'm using a vector 4f. We don't need the fourth value, so you can just assign 0f. It also gets the per instance take, also gets the get velocity grid. The num It gets the get velocity grid from our wind field instance. We we also have our pre-stage function, but before pre-stage function, we'll have a look at the consume per instance data for game thread. Uh, and this runs on is rendering thread, and this check is very necessary. Without this, Niagara won't know that this Unreal Engine won't know that this is the rendering. This function is supposed to be only ran on the rendering thread. First, we assign all the POD fields from our source data to the source data as in our render data to our target data in the WinField proxy. WinField proxy is the struct which is where all the GPU stuff will be happening, and this is a map to our proxy. Finally, we'll have a look at our pre-stage virtual function as well. This also runs on the rendering thread. What it does is what for instance tick does is it updates the double buffered velocity grid on CPU, and the pre-stage job is to queue the uploads, is to queue those uploads to the GPU structured buffer, the structured buffer that we defined in the set shader parameters and what we are using in the HLSL. And it also prepares the SRV for particle sampling. As you can see, this is where we log our velocity grid buffer. You don't want it to be changing at this point when the velocity grid SRV, when we are uploading our data to the velocity grid SRV, which is why it needs to be properly logged and unlocked. This is the stuff that does the queue upload to the GPU structured buffer. And to another important functions of the FNDI Winfield proxy. These are just both of them run on is in rendering thread, and they'll be the first function to first and the last function to execute. As soon as you run your GPU simulation, these two functions this will register your proxy with the Niagara data interfaces proxy. As I said, there is a map here, and you'll have a proxy somewhere in your code, and I have it in my post init properties. As you can see here, a make unique pointer of my Winfield proxy. Some people also have it in the constructor, but I prefer it to be in the post init properties because some of the inbuilt Niagara data interfaces have it there. There's an inconsistency. Some inbuilt Niagara data interface also have the proxy in the constructor, so choose what's best for you. And these are some of the important functions that I have for my RHI, init RHI. Sometimes if your RHI keeps getting called every tick, then you can't have a stable SRV, that a stable SRV or a stable buffer. Your data keeps on changing every frame, and before it reaches to your GPU or HLSL, it will only get the zeroed values, and it will never get the proper values, as the values will be flushed. So this is where all the stuff happens. You can see, unless there any elements have been changed, it just keeps on returning and never releases the buffer. And release buffer, you need an enqueue-render command to release the buffer. It shouldn't be done without an enqueue-render command. And this is the init RHI, what I was talking about. Uh, as you can see, this is the persistent GPU buffer, and this needs to be persistent, and so does the SRV. They both needs to be persistent. This is where also we create our SRV. As you can see, this needs to be created with an auto function. You can't create it any other way. If you just directly do the SRV desk, it won't work. You need to do it with auto. This is how the other data interfaces does it. This is the function that creates the SRV. We set it to the structured because our buffer is a structured buffer, and the stride needs to be accurate as well, which is f vector 4, and our buffer size is num elements into stride. So we need to create a shader resource view as well. Shader resource view is just our SRV, so that our HLSL and the GPU can see all the data that is included in the buffer, and the buffer that we are passing and the SRV that we are passing to the HLSL. And then we just release all the data, release RHI, and at the very last of our a very long custom Niagara data interface when field, we have this small function called post edit change property. As soon as any property of our custom Niagara data interface is changed, we just mark it dirty. So the Unreal Engine sees it, and we can save our custom Niagara data interface when failed because a change has been made, so it needs to be saved again in the Unreal Engine. So this is all the stuff there is in the custom Niagara data interface. And just a final look at .ush and what's being done here. And so that's all there is to this custom Niagara data interface when failed. Our custom Niagara data interface successfully with our Unreal Engine and Niagara editor. I'll show you how I use those custom Niagara data interface to influence my particles. So this is one of the many Niagara emitters where I'm using my custom Niagara data interface to influence the position of my particles. If you see, this is the NS snow template. As you can see, the particles moving based on my wind direction. My wind direction is currently 0.5, -10, and -1.0. So it's moving in the negative y direction as it should. And this is, I'll show you. This is the emitter hanging particulates. This is using CPU sim. Here is where you assign CPU sim. Whether you need CPU or GPU, you need to do it here. And this is the Scratch module that I was talking about earlier. This is the user parameter. As you can see, if you click this plus button, you can see a make new variable here, and you'll have a data interface drop down here. Under the data interface, these are all the Niagara's inbuilt data interface that it provides. And at the very end is my own data interface WinField. As you can see, if I hover over it, you can see Niagara data interface WinField written on it. So and as I said, it takes in a WinField instance. So you have to assign your Win vector field here to this, and this user dot WinField. Before I show you, before we connect, we need to do this in the ScratchPad input map. You need to get a map get node from here, which includes WinField and position. WinField calls the sample wind at location function. This is the function of our custom Niagara data interface. This is the function that it calls, sample wind at location. So this is the sample wind at location function of our custom Niagara data interface. As I told you earlier, this takes in wind field and particles dot position. We break this position into XYZ and feed it into the sample wind at location. This returns us the samples the velocities at that point and outputs it. We make a vector with the XYZ values and assign it to particles dot velocity. That alone won't change the position of the particles. For that, we need to get another map get node and use the particles position, velocity, and delta time. So we multiply velocity with our delta time, and then we have we multiply our velocity with our delta time, and then we have our position. So we add both our both are velocity into delta time, which is the delta move that we get with the particles dot position, and assign it to the new position. This is our new position vector, and we assign it to the position, and we can see the particles moving as they should be moving. You can tweak any of the values that you need here. I'll just show you if I uh, this is uh, this is currently going in the minus y negative direction, the particles. If I change this to 0 and I change the z value to 10, you can see the particles moving upwards immediately in the Niagara editor, as well as the viewport. You can see the particles going up immediately. As for the NS rain system, this is pretty much similar to the NS snow system. This is our NS rain template, almost uses the same ScratchPad, same setup, same user parameter. What's the difference in it? It's the splash, the raindrop splash that you see here. What I've done is add another emitter into it. I'm using a collision handler, event handler right here, and I'm using a generate collision event module. This module generates the collision event as soon as the particle hits. For that, you need to enable collision as well. As you can see, the collision module is enabled here. And in the next emitter, I'm using the event handler, and I'm receiving the collision in it here, right here. The collisions are being received here, and then I'm using just a sprite to, as you can see, this is a rain splash sprite, which generates a sprite at those positions. So and then we get to our GPU simulation. As you can see, they are moving in the negative wind bias direction. If I open this up and this GPU sim, this pretty much is the same thing as the NSNO I've showed you earlier. The only difference that it does is here in the same target, you need to choose GPU compute sim, and you need to choose fixed. The GPU sim doesn't work with the dynamic bounds. It either needs to be fixed or programmable, but most preferably it should be fixed. And just that is there straight to the GPU sim. This is what you need to enable, and it will start the GPU simulation of the particles. This brings us to our next Niagara system, which is the NX physics flames. So Phoenix flames. Now we will have a look at our another emitter system that uses the custom Niagara data interface wind field, which is the NX Phoenix flames. This is to create a phoenix fire body. As you can see, it kind of simulates the body of a bird. This uses a scratch module. The turbulence is set to 10. It uses sub UV animation. I needed a bit more smoother animation. As you can see, it's quite smooth the way it's moving. This uses a color module for the changing color of the flames, and just some other modules like solve forces and velocity. And the most important one here is the skeletal mesh location, because if you need to properly bind it to the to your skeletal mesh of the phoenix character, you need to assign assign the mesh here, and that's more than that. After assigning your skeletal mesh, you need to uh, attach it to the bowl properly. I've attached to the B spine, left wing, right wing, because that is where I want my flames to be, and not anywhere else. So after you have created this Niagara emitter system, what you need to do is include a component. This is the BP Phoenix character. This is your character, and you need to add Niagara component from here. As you can see, the Niagara particle component system, I've already added it here. And this takes in the NX Phoenix flame that I've created, this one. So, and as you can see, my Phoenix flame is perfectly attached to the Phoenix character, and the turbulence is making it look much better towards the fire on the Phoenix character. I'll play and show you how it looks in the game. So as you can see, the fire body of the Phoenix. With the NX Phoenix Flame done, this is all the places where I've used my custom Niagara data interface wind fields, NS Snow, NS Rain, NS Phoenix Fire Body, and just for the demonstrations stake, I've added a lots of snow particles here over the volcano, which makes it look a bit picturesque. And we'll look at we will have a look at how I did this. I need to remind you that this is not the this does not use the custom Niagara data interface any of this flame. This is an entirely separate Niagara interface system which is called NS Lava Fire, and this is purely for the to enhance my dissertation presentation. This includes 3 emitter, fire, smoke, and fire debris. The spawn rate is set to 30. The interesting thing I did is use the M Fire sub UV material provided by the Unreal Engine. I enabled the blending. I set the sub image size to 6x to match the sub UV sizes of the material. Then I'm using the sub UV animation. Same thing I'm doing with the NS Phoenix flames. Then just some other modules to make the flames look more realistic. And there is in the scale color and color just the same as NS Phoenix flames to make the flames look more to have different colors. And then the smoke. For smoke, we also do something similar. Unreal Engine provides us with M Smoke Sub UV materials, and I'm using Sub UV blending here. Same thing, 8x8 for Sub UVs. Sub UV animation. One thing I'm doing differently from the fire emitter here in the smoke emitter is the curl noise force. As you can see, 10,000 to make it look a bit more realistic. I'm making it at a low quality because this is just for the demonstration purpose and not anything visual. And then finally, the third emitter is the fire debris emitter. It's just a simple uses the default material, curl noise force, and the curl color gradient to have the debris at the top. As you can see, this is the flames, the smoke, and the debris at the top. Just below it, you can also see the lava flowing in the volcano. And how I did this is by just using a cylinder. This is called lava inside volcano. This is just a cylinder mesh on which I've attached the material. As you can see in the right panel, this is the M volcano lava material. What I'm doing here is using a motion purview chaos. This is the two texture object. I'm using a chaos speed which is set to 1. Motion purview chaos has been used both for normal and the texture sampling, and this creates a more lava undulating in the volcano, moving rapidly inside a volcano with the snow and the flames and the debris at the top, debris coming from the top, and for other things to make my dissertation look more presentable. I've used this water body river, which I've modified its material entirely. As you can see in the right panel, this is the main material river to lake transition. Uh, water material is the main material that influences this. So if I go to water material and then water material inst, then flowing lava material is the lava material that I created. I'll go in and show you how it looks. This takes inspiration from the water attributes existing one, which you can see. I've removed, there were lots of stuff here. I didn't need it, so I removed it and attached a scalar value to the absorption coefficient of the single layer water material. I removed a bunch of other stuff from here because I didn't need it. And the one thing I needed here is the lava attributes here. So this is where my lava attributes particle goes. This is the one I created. This is not at all similar to the water attributes. This is entirely created by me. It uses lots of things such as the panner node, absolute world positions, and moreover, this uses the noise and lerping between it. I'm using world aligned texture for all the texture objects, so it doesn't look stretched when used in the world. I'm using world aligned texture for the texture object, for the normal, for the roughness as but for the ambient occlusion, I'm using a separate world aligned texture separate channels node. As you could see, there are some blackish particles which makes it look like molten lava, and that is being done by this cheap contrast. I'm using another noise node, add it to the cheap contrast, uh, include a scalar parameter, saturate it, and then as usual lerp it between the main colors that are coming from over here from the panel node and the lerp, and then we lerp between this colors as well as this cheap contrast, that molten lava texture. So this is what we. So earlier I told you about the debug visualization that I'm using for my wind vector fields as well as uh, my local wind ejector. So I'll first show you mm, how I'm using a draw wind debug for my wind to visualize my wind vector field. Currently it's set to false and I'm using a branch condition for it, and this calls the debug draw method from the wind field instance. If I enable it and compile and save it, you can see the direction of the wind. The direction even if I don't currently I'm not pressing any buttons, WASD key. The Phoenix is entirely moving based on the wind, and if I do press any of the buttons. This is all. As you can see, the arrows are moving upwards. This is because of the local wind injector. The local updrafts are pace are assigned near the lava, so this makes the wind go upwards. So you can see my phoenix is going upwards. There are three local wind injectors placed near the lava, as as well as the volcano. Two near the lava and one near the volcano. You can see the arrows are slightly coming down because no local wind injector is placed here. Now this is back to using our global wind field. If I go towards the local wind injectors again, my phoenix will start moving upwards again. See, as I said, here are the local wind injectors are placed here. So my phoenix is moving upwards again as displayed by the arrows. So this was one of the ways that I'm using to debug my wind vector field and my just the wind vector field. I'm using a different debug for my local wind injector, which I'll show you in a bit. So here's my local wind injectors, and its name BP wind injector, which you can find here in the blueprints actors BP wind injector. It's all being uh, done from the class wind injector. This is a wind injector class. I'll show you the header first. This is how the header looks. It inherits from the A actor, and so I've exposed some of the functions, that I want to tweak to the Unreal Engine, like these debug values and velocity to inject and all that other stuff, and some of the functions that I'm using in the local wind injector. We'll have a look at the .cpp file now finally. Uh, some of these stuff is being used completely for the debug stuff. The main thing in a wind injector is the tech function. This is what does the job. I'm getting the actor's location, and this is the actor that I showed you earlier, BP wind injector. That is the actor, and it's assigns to the injector location, and then we call the inject wind at position function. We assign the injector's location to it, as in the get actor's location to it. We assign the velocity to inject, which can be set from either the code or the blueprint, as well as the radius, which can also be set from both way. And then this is the way I'm debugging it. There are a couple of you can either have the sphere in the editor or in the play mode. You can have in both, or you can have it in neither. So this is providing some extra boolean values in the editor, and show debug sphere. This is the main function which calls in draw debug sphere. Now, and what the one of the best things about this wind inject wind injector is that even if you move your wind injector while the debug sphere is there, the debug sphere will reset all the lines. As you can see, for that I'm using draw temporary debug sphere, which sets the previous debug spheres to false, and it calls the new draw temporary debug sphere by setting the previous ones to false right here. So you have a debug sphere at the new position. So as you move your wind injector in the Unreal Engine, you can see the debug sphere moving as well. So this is one of the interesting things that I've done in the wind injector, and that is all there is to this local wind injector. You can assign this local wind injector to many other things. I've just assigned it to simply BP wind injector, but you can assign it to the grass or the tree or wherever you want it to be. So so as you can see, this is my BP wind injector. Now I'll show you if this is false. So as you can see, this is my BP wind injector. If you enable it, you can see the debug, the local wind injector moving, and you can see the debug lines being flushed and the new lines being created at the same time. So this is a nice quick way to debug your local wind injector the way you wish to. If you click the show debug sphere always in editor, you can see it's being shown always in the editor, and as you move it's still there. So this is a quick way to visualize and debug local wind injector.